Here we are for AP Physics Motion Miscellany. I just want to do problem 4, right? Yes, that's the Carnival Game 1 projectile problem. Just real quick, just run through it. It's actually just kind of doing 2 projectile problems in one and looking at the difference between them. So problem 4 says, a popular carnival game is to throw quarters at a set of glasses on a table a few meters behind the counter. A quarter is thrown from a height 1.1 meters above the glass at an angle above the horizontal. Let me kind of sketch that out here real quickly. So we are going to launch our quarters. Right. Launch them. Flip. Here we go. At an angle that is 53.13 degrees above horizontal. They're going to go right, and they will hopefully land in this little shot glass. Okay, that's down here. And if we throw at one speed, it'll just barely land in the near edge of the shot glass. Throw it just a little bit faster, and it'll go a little bit farther and land in that far edge. Whoops. Make that shot glass a little bigger. There we go. In that far edge of the shot glass. So if we go ahead and throw in the data that we know, I'm going to say, hey, I know that top edge of the glass we know is 1.1 meters below where we're throwing the quarter from. We know that the near edge here is a distance, it says 3.175 meters away horizontally. And the far edge is 5 centimeters more, so that's 0.05 more. So that will be 3.225 meters away to get to that far edge, right? Yep. Okay. And then what else do we know? That's really about it. Right? So that's the setup. So we want to know what the speed has to be for it to land at the near edge and the speed for it to land at the far edge. And so we can see how much range of speeds we have to work with here. And so what I'm going to do is I'm going to make my chart of my X and Y information. Okay, and I'm going to set this up for launching to the near edge of the cup first, of the shot glass first. So here we go. I'm going to make my chart. Horizontal information and vertical information. A, V naught, V. I can get rid of this now. A, V naught, V, delta XT. Okay, A, V naught, V, delta Y. Wonk, wonk. Wonk, wonk. We know the acceleration of the X is 0. We know the acceleration of the Y is going to be a negative 9.8. Okay. What else do we know? Well, if we're going to the near edge, let's see here. We know the initial velocity. I'm going to take this initial velocity and split it up into components. So I'm going to say that initial velocity will go right? And so this will be V cosine 53.13 and V sine 53.13. Okay, and so I can fill those in here. V cosine 53.13 degrees, V sine 53.13 degrees. We don't know anything about the speeds when it hits, the velocities when it hits the cup, the glass down here. So we don't know the V's, but we do know the horizontal displacement. Okay, for our near edge, that's going to be 3.175 meters. And I suppose I should be putting units on this too. Okay. And let's see here. And for our vertical displacement, we're going to go down 1.1 meters. I'm going to make that minus 1.1 meters. All right, so that's what I know. So when I go to pick formulas, we all know that in the horizontal axis, we are going to be using delta x equals vt, okay, because the acceleration is 0. So it's the constant velocity equation. That's for our x-axis. And so that'll look like 3.175 equals v cosine 53.13 times t. Okay. And then in the vertical axis, on the y-axis, we're going to say, well, I'm trying to find v. I need to get rid of t. So I need another equation that has t in it. But the thing is, well, why not? Yeah. Use delta y as v naught t plus 1/2 at squared, right? And I can solve for that t. Huh. So if I do that, right? So I'm going to have the equation minus 1.1 equals v sine 53.13 times time, and then half of negative 9.8. I'm going to do minus 4.9 t squared. All right. See, I just barely squeezed that in there, right? And you can almost read what it says, so that's pretty good. And so now I've got two equations that have v and t, right? The v, again, is that hypotenuse, so it's the same v in both, and the t, because I just took the components out, and then t is the same time in both. Time to go from here to here, horizontally and vertically the same. And so that means I can sub and solve to get rid of. We want to get rid of the t and just get v. So what I did, I chose to, now it's just algebra. It's just algebra from here. I'm going to rearrange this one to get t by itself. So my t will be 3.175 divided by v cosine of 53.13. Makes me wish I'd kept that as a theta until just put the 53.13 in at the end to make it a little tighter. But that's okay. We'll just suffer through. Now that I have this expression for t, I'm just going to take this expression and substitute in where I see t, there and there. Okay. So that's going to get me some gnarly looking expression that I'm going to jam into this little space because what are you going to do? All right, I tell you what. I'll just, the 53.13, I'll just call that theta. That'll save me this much space on the paper, which will make all the difference. I'm going to bring this over here. So I'll have minus 1.1 equals, now I'll have v sine theta times t. But where I have t, I've got this, right? So I'll have a 3.175 over v cosine theta, right? Okay. And you say, no, wait a minute. Wait, that's okay. It's okay. See, I'm running out of room. See, that's, and then I'm going to have a minus 4.9 times this thing squared. I hate having to go under like this. Minus 4.9 times this thing squared. So that'll be 3.175 squared over v squared times the cosine squared theta, right? Yep. Okay. So the key thing, the cool thing I want to point out here is that when I took this v sine 53 times t, but t has, see the v's in the bottom? So I've got a v in the top and a v in the bottom in that term. So the v is going to drop right out. Whew. So the only v I have is in this term here, which means, and everything else is the only variable, I can solve for v relatively easily. I'm not going to have to do some kind of crazy quadratic or anything. It makes me happy, you know? Not that I can't solve a quadratic, but anyway. So I've got, this is a negative term, this is a positive term, this is a negative term we're subtracting here. I'm just going to subtract this term over to the other side so I can combine those constant terms. I do know the value for theta, right? Move that over here. So when I do that, I'm just going to move over here. I'm just going to move over here. I'm just going to move over here because I'm running out of room. So I'm going to have this minus 1.1 minus, you know what sine over cosine is? That's right, it's tangent. I'm even going to put the number in, 53.13 times, times 3.175, right? Okay, that's what's on one side. On the other side of the equation, I have this mess, negative 4.9 times 3.175 squared over v squared cosine 53.13 squared. Okay, so the key is this is a number. This is all numbers I can get my calculator. I'm just going to solve for v squared. And you see there's a negative, and there's this, negative, negative, negative. I can make them all positive, right? I can flip all these signs, multiply through by -1. This all becomes positive, 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 right? I don't have to worry about those negative signs anymore. And so when I solve through this, right, you don't need me to do, I'm just going to go ahead and combine those in my calculator. And then I'm going to divide both sides by the numerator of this. And then I'll take the inverse of both sides and then divide through by cosine squared of 3.3 and then take a square root. When I did all that, I'm not going to do all the algebra. I'll just tell you what I got. When I did that, I get 5.072 meters per second. Okay. So there was like a 1 or something after that, if I remember right. Anyway, 5.07213 or something like that. Okay, so that's what I get. So that's the near edge. That's the speed it has to get flipped at in order to land at the near edge. The far edge, it's going to be the exact same calculation, except everywhere I see a 3.175, I'm going to put in 3.225. You know what I mean? Of course you know what I mean. And so that'll show up here, right? Yeah. Which then gets transferred through. So that's a 3.225, and that's a 3.225 squared, right? And into here. And so I can get all the way to this. I can go all the way to this step. And just here, make that a 3.225 instead, and make this one a 3.225 that's getting squared in there instead. And do the calculation, and you get 5.1201 meters per second is what I got. And so you say, hey, how much is that different by? And you say, look, that's a teeny tiny difference in speed. If you're going to flip at the same angle, right, then you have to launch at a slightly different speed for it to go a little farther. But look at how tiny that changes, right? And you say, if I went ahead and I did like a percent difference, right? So like this difference, do you want to do this difference is what percent of the original speed? Sure, why not? So I do 5.1201. You're going to ask why I went down to the digit on this one and that one. I don't know. I just happen to have it ready. Minus 5.072, right? And I divide out of 5.072 times 100, right? To make it a percent. And it's 0.948. It's less than 1% difference, right? Less than a 1% difference, nearly a 1% difference in velocity needed, that you have that much leeway to make it hit that class. And that, my friends, is how they make money on these games. At least part of it, anyway. By making something that looks like it might not be so hard, but really is actually very, very difficult to do. It's a very small tolerance you have for speed to hit that. Now, the fact is, you can change the angle too, or you're going to be, no, just stop right there. But the point is, yeah, they're harder to do than they might appear. Okay, that's it for problem number 4 from the motion miscellany sheet.